Very good morning, students. In today's lecture, let us look at the soil embankments that are supported on Geocell matrices. The brief overview of today's lecture is, in the previous lecture we have discussed about the optimization of the reinforcement layers, so that we can economize on the reinforcement that is provided, and then we will look at the design of embankments that are supported on Geocell matrices. In the previous lectures, we have seen the design of a steep slope that is resting on hard foundation soil using planar wedge analysis, and we have seen that we require 16 layers of reinforcement layers, and which were provided at a spacing of half a meter vertical spacing, and the slip circle analysis gives us a factor of safety of 1.71, and we have also seen that this slip circle can be represented more appropriately using a bilinear wedge or a two-part wedge analysis, and which we have seen that which is more appropriate, because all the embankments are built using granular soils, for which the planar rupture surfaces are more appropriate than curved rupture surfaces, and we have seen that we can redesign that slope using the two-part wedge analysis, and we have the design quantity of reinforcement was 10 layers of reinforcement layers, each having a strength of 25 kilonewtons per meter, and they were provided at very large spacing, 1 meter spacing, and we have adjusted the 10 layers within the 9 meter high embankment, and the slip circle analysis gives us a very low factor of safety, 1.16, which is unacceptable. Normally we require at least 1.4 to 1.5 for slopes that are carrying permanent highways and railway embankments. So, we need to redesign this, and so we can actually, by decreasing the vertical spacing, we can provide 14 layers, and here we see that when we provide 14 layers of reinforcement, all having tensile strengths of 25 kilonewton per meter, the factor of safety increases to 1.44, and the reinforcement layers were provided at half a meter spacing in the bottom 3 meters, and 0.75 meter spacing above that level from 3 to 9 meter height, and the factor of safety is 1.44. and let us see whether we can do some optimization, and actually it is an iterative process. We can use a computer program and come out with more efficient alternatives, but here I have considered only two types of reinforcements, one having a strength of 25 kilonewton per meter and the other having a strength of 15 kilonewtons per meter, and in the top 6 meters 12 layers were provided having a strength of 15 kilonewton per meter, and in the bottom 3 meters stronger Geo Grid layers having a strength of 25 kilonewton per meter are provided, and the factor of safety is 1.41, which is very nearly equal to the previous case where we had provided 14 layers all having 25 kilonewton per meter strength. So, it is actually the factor of safety of 1.4 is a reasonable value that can give adequate safety for the embankment, for the long term performance of the embankment. So, at this point we should realize that it is possible to redistribute a given quantity of reinforcement uniformly over the height of the embankment and come out with more efficient solutions, and this 1.41 is obtained with 12 layers of reinforcement layers having a strength of 15 kilonewton per meter and 7 layers of 25 kilonewton per meter strength, and we could actually do some more trials and see whether we can get similar factor of safety, but with having more combinations of the reinforcement layers. Okay, that we can try later on through some computer programs. And now let us go to the topic of today's lecture, that is the construction of the embankments on Geocell matrices. And the concept for the design of Geocell matrices, it goes way back to the Skempton's analysis, who showed that for smooth footings the shear deformations are outward deformations. Like for example, here if this is the center line of our footing, and if we apply some loading on a smooth footing where there is no friction between the footing and the soil, the deformations are outward, and he showed that the bearing capacity, because of this it can reduce. The NC factor of 5.14 is for a rough rigid footing, but if we have a smooth footing, it is possible in some cases we can have a strength the NC factor less than 5. That means that as we make the footing smoother, our bearing capacity reduces. On the other hand, if we have a rough footing wherein the deformations are inwards, that is towards the center, and he showed that in this case our bearing capacity factor NC is proportional to the footing width. That means that as your footing width is increasing, your bearing capacity increases, and this is what is shown here for different cases of the B, that is the footing width, and SU is the undrained shear strength of the soil. The bearing capacity shoots up as your footing width increases. This rho B by SU is a non-dimensional number, and we see that there is a drastic increase in the bearing capacity of the soil when we have a rough rigid footing. And this concept can be explained like this. Let us say that we have an embankment that is resting on a Geocell mattress like this, and we have a thin soft clay layer, and we have a rigid foundation at the bottom of the clay layer, and the plastic failure conditions is more similar to squeezing of the clay between two rough rigid platens. And here is on the left hand side we see the Geocell mattress being fabricated, and this particular photograph is from the design manual of Tensor company UK. The thin layer of soft clay between the relatively rigid Geocell layer and the rigid foundation layer is similar to the plastic material which is between two rough rigid platens, and for this case the plasticity solution was proposed by Johnson and Meller in 1983 in their book on engineering plasticity, and who derived the slip line fields for deriving the bearing capacity or the bearing pressure, the maximum pressure that we can apply on the platens. And this procedure can be applied for the design of Geocell mattress for the construction of embankments on thin soft soil layers. And this particular procedure that we are going to discuss is only applicable for the case where the embankment base width is greater than 4 times the thickness of the soft clay layer. Actually this is our embankment base width is B like this, and the height h of the thin soft clay layer, and the B by h should be at least more than 4 for us to apply the theory derived by Johnson and Meller based on the slip line fields. And there were 2 excellent papers that summarize the extension of this procedure for the design of the Geocell matrices. One was published by 1988 by Jenner, Bush and Bassett. The title is "The Use of Slip Line Fields to assess the improvement in bearing capacity of soft ground given by a cellular foundation mattress installed at the base of an embankment. This was presented at the symposium on theory and practice of earth reinforcement, and there is a subsequent paper in 1990 by Bush, Jenner and Bassett, and the design and construction of Geocell foundation mattress supporting embankments over soft grounds. Actually, the first paper is more on theoretical aspects on how to adapt the slipline field method for calculating the bearing capacity improvement below the Geocell reinforced embankment, and the second paper is more on how to apply that theory for the design, and then they have also shown the application of this method for construction of a large size embankment, and they also provided lot of field data in this paper, and they claim that this method of design is quite successful in many situations where they have achieved uniform settlements, and the bearing capacity was found to be much higher than what it would be otherwise without our Geocell mattress. Well, basically the Geocell mattress, it acts like a very rough and rigid the platen, and it prevents lateral outward movement, and thus it rotates the principal stress directions. So, without this without the Geocell mattress, if there is only embankment, the principal stresses, we can say that the major principal stress is vertical and the minor principal stress is horizontal, and that may remain so because our embankment is relatively flexible in the absence of any Geocell mattress, and we can assume that there will be lateral outflow of the soil, and then we form the normal slip circle. But in this case, because of the roughness of the Geocell mattress, the outward movement is prevented, and the direction of the principal stresses is rotated, and even the direction of the maximum shear stresses also rotates, and the result of all this is that our failure surface is pushed deeper into the foundation soil, thus increasing the bearing capacity, and that is the main principle of this procedure. And once again this photograph is from the Tensor design manual, and here we see that we have an embankment resting on a thin clay layer, and these are all the slip lines, slip line fields that we can draw. Each of them is drawn at 15-degree intervals, and the Terzaghi's bearing capacity theory says that our the NC factor P by Cu is 5.71, and because we are preventing the formation of the plastic failure surfaces because of the rotation of these plastic the slip line fields, our bearing capacity factor goes on increasing. For very thin footings or very narrow embankments up to maybe about a B by H of about 1, our bearing capacity factor is nearly equal to 5.7, but we see that as our footing width is increasing, the bearing capacity increases, and it attains maximum value of about 16 to 17, but for this particular case depending on the width of the embankment, in this particular case our bearing capacity factor is increased to 14, which is quite substantial because the normal bearing capacity is 5 times Cu, whereas here now we have 14 times Cu, it is almost an increase of 3 times, and more importantly we can expect uniform settlements because of the provision of this the relatively stiff Geocell mattress. And the equation that explains the stress redistribution and the increase in the bearing capacity is given like this. Here the P by Cu is the value read from the stress field at the extreme end, that is our 5.7, and then this internal quantity, this 2I plus 0.5d by 2x, the I is the sum of the horizontal chord lengths times the rotation of the slip line fields, and the x is the net sum of the horizontal chord lengths, and d is the depth of the soft soil layers, and in principle this is obtained like this. So, actually let us consider 4 slip line fields A, B, C, D, and the chord lengths AB plus BC plus CD is the chord length, and the rotation is basically this is the rotation 15 degrees, 15 degrees and 7.5 degrees, that is totally 37.5 is the rotation that is undergone by the slip line fields, and this type of calculations need to be performed for the given case of width of the embankment, and then the thickness of the soft clay layer, and then we have to estimate the increase in the bearing capacity factor. The solution looks something like this. Basically we plot a graph by drawing the embankment and the geocell to some scale, and then we superimpose the slip line fields, and then we can read off the increase in our bearing capacity factor. And now let us see some practical aspects on how to construct the geocell layer, and the geocell layer is usually constructed out of biaxial type geo grids. The biaxial, as we know, those are the geo grids that have significant tensile strengths in both the principal directions, and here we see that we have typical biaxial geo grids. The rib width seems to be the same in both the directions, and the aperture opening is also the same, and here we have the geo grids that are cut to required height and assembled at the site, and at the bottom we have a geo grid layer. This basically the bottom geo grid layer acts as a separator, and when we infill this these geocell mattress with some granular material, the bottom layer prevents the separation or the downward flow of this aggregate. And actually when we construct these geocells, they are all empty, and now we need to fill them with some aggregate or some granular material, and we need to carefully do that filling, because otherwise if we fill it randomly, we may not get uniform consistency, or we may not get we may damage the geocell layer, and the suggested procedure is like this. We fill the aggregate only to some small height, and once we fill one pocket, we fill the neighboring pockets to the same height, and then we can increase the height of the aggregate in the first pocket, and then we can increase the height in the next pocket, and then we can fill the subsequent neighboring pocket, and so on. And after all the geocell matrices are filled with aggregate, we can have the normal vibro rollers to compact the entire layer, so that we get good compact fill. And the procedure for constructing these geocells in the field is something like this. So, if we have a soft clay foundation, usually we need a working mat, so that we can bring in our construction equipments, and that working mat will be in the form of sand layer or some aggregate layer. Then we will provide a horizontal layer of geo grid that acts as a separator, so that the infill material that we fill in the geocell mattress does not escape into the soft foundation soil. And then we construct these geocell these layers, vertical geo grid layers. The procedure is something like this. This is a plan view. We lay the geo grid separator on the ground, and then we have these transverse geogrid layers that are constructed, and for this purpose we need to provide some supports along the length, like this what we see here. These are all called as the Bodkin joints, and they also provide some vertical support for the formation of this geocell. So, after we construct these longitudinal geogrid layers, we can now connect the transverse members. Okay, the transverse members, and then once the whole thing is the entire matrix is assembled, it is ready for filling with aggregate, and this is what we have. This is the soft clay foundation and the geocell layer filled with aggregate, and then our embankment. Well, in this lecture I want to briefly present some experimental results that we have obtained at IIT Madras based on some laboratory tests. Here we have taken a soft clay soil of 600 depth. The length of this tank is 1.8 meters, and it is filled with soft clay soil almost at liquid limit consistency, and which has a CBR of 0.5, and the undrained cohesive strength that we get from the vein shear test is about 3 to 5 kilopascals, very low strength, and the consistency is such that if a person stands on this clay, they just simply sink up to the knees. Then on this soft clay layer, one layer of geocell was spread of height h, that itself is a variable that we will see, and on top of this clay sand embankment of height 400 and to simulate higher height embankments, the uniform pressure load was applied, and this uniform pressure load was distributed evenly by providing some EPS layers, and then there was a thick steel plate, and then the load was applied through a proving ring and hydraulic jack. Measured 3 vertical deformations. There is one here, there is one dial gauge just behind this proving ring, and there is one more dial gauge here, and then the horizontal deformations within the height of the embankment, and then the heaving of the foundation soil was measured at the far end of the tank through this dial gauge. And here we see the formation of the geocell mattress, and then filling with the soil, and 2 types of infill materials were considered. One is the granular soil material, and the other is soft clay material itself. And here we see the formation of the embankment that was done with by compaction, and here we see the constructed embankment. This is the embankment slope, and this is the top surface, and the embankment was constructed using a soil. It's a clayey sand, so it has got some cohesion of 10 kPa, and the friction angle of the fill soil was 30 degrees, and the unit weight was approximately 19 kilonewtons per meter, and the very large number of laboratory tests were performed by varying different parameters. The first parameter that was varied was the tensile strength of the geogrid that was used for fabricating the geocells, and the height of the geocell layers. 4 different heights were considered: 100 150 200 and 250 and then the pocket opening size of these geocell layers that we call as aspect ratio, and then the pattern of formation of the geocells. There are 2 patterns, one is a diamond pattern and the other is a chevron pattern that we will see through a slide later. And then the length of the geocell layer, the full length means the geocell was provided over the full length of the tank, and then the truncated length means the geocell is provided only up to the toe of the embankment. That is normally what is done in the field. Then the type of soil infill in the geocell pockets, the clay soil and the clay sand. Then 2 depths of foundation soil were considered, 600 mm and 700 mm, and then the separator layer, the effect of geogrid layer at the base, and the reinforcement within the embankment soil. And the typical load strain behavior of the geogrid layers is like this. There are actually 4 types of geogrids were used for fabricating the geocell. 2 of them are very soft meshes, which are called as NP1 and NP2. They have a tensile strength of hardly about 6 to 7 kilonewtons per meter, and their peak strength is developed at very large strain, anywhere from about 15% to 30%. Then there was a biaxial geogrid with a peak strength of about 20 kilonewtons at a strain level of about 20%, and then the uniaxial geogrid that has peak strength above 40 kilonewton per meter, and that develops at about 25% axial strain. And 2 patterns were considered for formation of the geocell. One is the diamond pattern, that is what we have seen earlier in the animation. Each of these is like a diamond. Then chevron pattern, this is like a half diamond shape, and we use a Botkin joint to support or to form these vertical joints. Like this, we have a plastic rod, and we have the geogrids going in different directions, in the length direction and then the transverse direction, and we attach them by passing the geogrid through each other through these aperture openings, and then we insert this plastic rod in between to form the joint. These are all the joints, these dots, they are all the joints. And in plan view, this is the view, and 2 types of pocket openings were considered. The tank width was 800 mm and the length of the tank is 1800 mm, and the spacing of 200 mm like this dimension, and then 100 mm, and the triangular opening space that we get, that was converted into an equivalent circle just for the purpose of calculating the aspect ratio and other things, and the equivalent diameter corresponding to this triangle was used in all our calculations. And the 2 cases of embankment lengths considered, this is the full length case, wherein the entire length of the tank was covered with a geocell, and the other is the truncated geocell, wherein the geocell was provided up to the toe of the embankment like this. And all the tests were performed by having a perspex sheet on one side of the tank, which is transparent, and we can observe the internal deformations. And with NP1 type of geogrid reinforcement, the slip circle was something like this, and NP2, interestingly, it has the same the similar tensile strength, but then its opening sizes, the aperture opening sizes are much smaller, and the performance with NP2 geogrid was almost equal to that of the the uniaxial geogrid, and the effect of using a stiffer geogrid layer for forming the geocell is that the slip surface is pushed down, and when we used a very stiff geogrid UX geogrid, actually the slip surface was intersecting the tank foundation, and so the result of this the different slip circles is reflected in the amount of pressure that we can apply, and these are all the the different results that were obtained from large number of tests. In the first column we have the type of geocell material, the unreinforced one, wherein there was no geocell mattress, and the maximum pressure that we could apply on top of the crest of the embankment was about 50 kPa. So, actually if you recall, the pressure load was applied like this, and the pressure was applied in small increments, and the usually about 3 to 4 kPa pressure was applied, and then we wait until the deformation cease until under that particular pressure increment, and then only we go on to the next pressure increment. It was done at a fairly slow pace, and the unreinforced embankment failed at a pressure of about 50 kPa, and when the geocell was made of uniaxial Geo Grids of height 100 mm, that has a aspect ratio of height to diameter of 0.44, and the pattern of geocell was diamond pattern, and the surcharge pressure capacity has increased to 95 kPa, and then if there is no subscript for the type of geocell material, that means that the geocell pockets were filled with clayey sand, and there were some tests performed with clay infill. For example, the BX, that is the biaxial with 100 mm height, this is the second one. When the geocell was made of biaxial geogrid, that has a lower strength and the same height of 100 mm and the same aspect ratio of 0.44, the maximum surcharge capacity was only 75 kPa, and when the same configuration was used, but the infill material was clay soil instead of clayey sand, the maximum surcharge pressure that could be applied was only 65 kPa, and then as the height of the geocell mattresses were increased, the surcharge capacity has increased, and more importantly, it is we found that it is not just simply the height, but the aspect ratio, that is the ratio between the height of the geocells and then the equivalent diameter, because the h by d ratio more or less defines the stiffness that the geocell system can provide, because for very small values, like for example, the small value means very large pocket sizes, in which case the vertical geogrid layers will not have adequate restraining effect, and they behave like much softer materials. So, our for BX of about this 1.1, the surcharge capacity was 95, and for one case where the aspect ratio was about 0.9, the surcharge capacity increased to 110. The height in both the cases, say this case number 3 and this one with a star, the height is the same 100 mm, but the pocket opening size is different. In this case the aspect ratio was 0.44, and in this case the aspect ratio was 0.89. The result is substantial increase in the surcharge capacity, and so these are all the results from different analysis, and we see that the surcharge capacity not only depends on the type of the geogrid that was used, but also on the aperture opening sizes, and then the size of the geocell mattress openings. And these are all the results that we have. The UX is the uniaxial geogrid that has a slope of the m is the modulus about 200 kilonewton per meter, and obviously this has given the stiffest response, that is for a given surcharge pressure the settlement of the embankment supported on UX type material is the least, and this is the bottommost one is the unreinforced one, and it has the highest settlement, and all these results were obtained with height of Geocell of 100, and we see that both NP1 and NP2 they have the same modulus of 70 kilonewton per meter like this, but then one of them, the NP2 has smaller aperture openings, and because of that the strength is slightly higher, and actually here we see that in all the tests done with NP2 Geo Grid, the slip surface is pushed deep into the foundation soil, and these results they show the lateral deformations, the surcharge pressure, and then lateral deformation on the y axis, and all the results pertain to the case of 100 mm height of the geocell. When we have the geocells made of uniaxial geo grids, the pressure is higher, and then the deformations are smaller, and here on the extreme side we have the unreinforced embankment which has undergone largest deformations, and in between we have this biaxial geogrid, and then NP1 and NP2, and these results they show for the results for 100 mm height of the geocell, and these results they show the heave that is measured at the far end of the tank, and obviously with unreinforced embankment the heave was the maximum, almost 25 millimeters, but when the geocell made of uniaxial geogrids was provided, the heave was reduced about 7 or 8 millimeters, even at a much higher pressure of 140 kPa, and for the other geogrids it is somewhere in between, and the results with different height of geocell layers, and each height of the geocell layer will result in a different aperture opening size, because all the equivalent diameter of the geocell pockets was 226 millimeters, and this height divided by 226 is listed here. When the height is 250 mm, the aspect ratio is about 1.1. It has probably the best performance in terms of the lateral deformations. Then as the aspect ratio decreases, the lateral deformations were found to increase. Then of course the unreinforced embankment has the highest lateral deformations, and these are the results that are obtained with the same height of the geocell, but with two different aspect ratios, 0.89 and 0.44, and this is the result with a stiffer geocell mattress. As the aspect ratio increases, we have the pocket size decreasing. That means the stiffness of the geocell mattress increases, that results in higher load capacity and the smaller deformations. And this graph, it shows the two results that were obtained with the same aspect ratio of the geocell, but with two different depths. Like here the green color symbols indicate the result for height of 200 mm and the pocket opening size of 0.4 meters, and the equivalent diameter is 226 millimeters, and this is height of 100 mm, and then the equivalent diameters was 113 millimeters, and both of them they have H by D ratio of nearly the same 0.89, and we see that the lateral deformations were almost the same. That means that the aspect ratio of the Geocell pocket openings is very important, and that should be one of the design factors that need to be considered. And to actually see how the Geocell is responding as the pressure is gradually increased, we have measured the strains that are developed in the Geo Grid layers at different stages. These were all the locations where the strains were measured: S1, S2 and S3. These are the strains that are measured in the longitudinal Geo Grids at different heights. S1 is in the below the load, S2 is near to the toe of the embankment, and S3 is away from the embankment, and S4, S5 and S6, they are the strain gauges to measure the reinforcement strain on the transverse ribs. Once again, S4 is below the loaded area, S5 is near to the toe, and S6 is away from the embankment. And this is how all the strain gauges have responded. As the surcharge pressure was increased, initially there were negligible strains. That means that the Geocell has not really started taking the load, because the soil itself was strong enough to take the pressures, and gradually as the soil was failing, we could observe the formation of the slip surface, and that is when the effect of the Geocell layer got kicked in, and then we started seeing the increase in the reinforcement strains within the Geocell layer. And these diamond shaped, one is the strains under the load is actually as much as 3% strain was measured, and the plus sign is near the toe, and outside the embankment is the star, and the strains that are developed in the Geocell layer outside the embankment are relatively small, whereas below the load and near to the toe they are of comparable magnitude. And these are the strains that are developed with the different materials. The UX is the uniaxial geogrid that has the lowest strains, because its modulus is the highest, it is much higher. Actually the modulus is 200 kilonewton per meter, whereas the biaxial, the diamond shape, it has the modulus of about 160 kilonewtons. Then NP1 and NP2, they have much lower modulus values of 70, and the strain that is measured was found to be related to the modulus of these the geogrid layers, and the stiffer geogrid layer has developed a smaller strains as compared to the softer geogrid layers. And the summary is, we have seen that the use of Geocell layers below the embankment enables the mobilization of higher bearing capacities. This is mainly because of the rotation of the principal stress directions, and it prevents the formation of the normal slip circle. And if we form a normal slip circle, the bearing capacity factor is about 5, but in this case, because of the provision of a very stiff Geocell layer, and the action is similar to the squeezing of clay in between two stiff and rough rigid platens, the principal stress field itself gets rotated, and we end up with higher bearing capacities, and the settlements that we have below the Geocell reinforced embankments are found to be more uniform, and we need a very good quality infill for the Geocell to be effective. And the slip line field plasticity solutions leads to good designs. Is actually those students who are interested can refer to the papers that are listed, and some field data is given in those papers, very interesting field data. that show that the Geocell reinforcement has actually increased their performance in terms of uniform settlements and lower settlements. Okay. So, thank you very much, and if you have any questions you can contact me on the email. Thank you. Bye.